So we're now going to shift our focus from completion service and executor service and the executor interface, all the executor stuff we've been talking about, and multi-threading and thread pools, and begin to talk about some of the core Java synchronizers, starting with perhaps the most fundamental one, which is the Java ReentrantLock. So before we get into the details of ReentrantLock, however, let's first take a little detour and discuss some of the underlying concepts that motivate the need for ReentrantLock. And this will focus on the support that Java provides, and more generally, concurrent programming techniques and languages and frameworks provide with respect to mutual exclusion. So we'll start off by talking about what mutual exclusion is. And after I give you kind of a conceptual overview of mutual exclusion in the context of the technologies we'll be working with in this course, I'll also give you a somewhat memorable human known use of mutual exclusion that you've probably encountered before if you've ever flown on an airplane. So let's first start by talking about mutual exclusion, and in particular, mutual exclusion locks, which are sometimes known colloquially as mutexes for mutual exclusion. And a mutual exclusion lock, or a mutex, is used to define a so-called critical section. And you can read more about critical section at the link at the bottom of the page, but essentially a critical section is a group of instructions or a region of code that must be executed atomically. And as I talk about a critical section, I'll go and compare back to what we talked about earlier with respect to atomic operations like atomic locks or the volatile type qualifier, because those are limited forms of mutual exclusion. The way that mutual exclusion works with a mutex is only one thread at a time can execute a block of code. And so this gives you mutually exclusive access in the so-called critical section. The way this works is that a thread comes along, it says, hey, lock, are you available to be acquired? And if the answer is yes, then it acquires the lock, and that thread then goes and starts to run in the context of the critical section. And that's the only thread that can be in that critical section as long as all the threads follow the locking protocol. All the other threads are kept at bay. They have to wait. They have to essentially queue up or spin or do something while the other thread is running. And the reason for doing this, of course, is pretty obvious, I hope. You want to prevent corruption of shared mutable data that would otherwise be able to be set or get by multiple other threads that are running concurrently. So we want to make sure that we don't end up with data collisions, read-write conflicts, write-write conflicts, various conflicts that you can have that will corrupt the state of shared mutable data, which, as you know, is the root of all evil in concurrent programs. Now, the thing to remember is that this whole thing only works if all the threads obey this locking protocol. All threads follow the path of grabbing the lock, waiting to get the lock if they can't get it immediately, and then taking turns to go in there. If threads decide not to follow that protocol, either usually by accident, but if they do it maliciously or intentionally, chaos and insanity will ensue. And believe me, this is very unpleasant experience if you're trying to debug your code with concurrent race conditions, especially if you didn't write the code, because it's very, very hard to track down. Now, what happens if you don't follow the protocol is you'll have things called race conditions. We've talked about race conditions before, and they're basically problems that arise whenever a program depends on the sequence or the timing of the threads in order for it to operate properly. So sometimes you get lucky, but most of the time you don't get lucky, or most notably, you don't get lucky when it really matters, when you're giving a demo for a customer or the airplane is about to land or something, something catastrophic will happen and you're not going to enjoy the outcome. After a thread leaves a critical section, another thread can enter the critical section and it can start to run. And so basically the way that works is the next thread will have to acquire the lock, just like the first thread had done, and then it enters the critical section, and that thread then gets exclusive access to the shared mutable state within that critical section. Now, if you think back to the way that atomic operations worked, they also have critical sections too, but those critical sections span a manipulation to a single value, like a volatile setting or getting it, or an atomic operation on an atomic integer or atomic long, where you're going to increment it or decrement it. And so the critical section is incredibly narrowly defined as basically the update or the set or read of a particular object. When we talk about mutual exclusion locks, you can have a wider span of the critical section, which can encompass multiple instructions or multiple statements. Whereas for the atomic operations, you only get to do them on basically one object or one operation. Internally, a mutex is typically implemented using atomic instructions, atomic operations like compare and set or compare and swap or test and set. And as we've talked about a number of times before, atomic operations either happen all in one fell swoop or they don't happen at all. So they have certain nice properties about atomicity and consistency and visibility and ordering and so on. And we've talked about those things before, and you should be responsible for understanding those properties pretty well because we've covered them in detail. Under the hood, in Java, they're implemented using these compare and swap methods that are part of the Java unsafe class or its modern equivalent. That class is gradually being deprecated for use internally and replaced by other things. But for now, that's kind of the way to think about it. And those are very important operations because they're designed to be extremely efficient and they use hardware level instructions to do their thing. So I promised you I would give you a quick memorable example of mutual exclusion locks. And we've talked about this before, but we're going to actually walk through it from a protocol point of view now. And the example is going to be the protocol for accessing an airplane restroom. So I'm sure if you've ever flown in an airplane and you had to use the restroom, you know the protocol. The way it works is you walk up, and if there's a line of people waiting for the restroom, you stand in line. And the way it works is when the restroom is available, it'll say, available or free or open or whatever. And you go in, and once you're in, you shut the door and push that little slider lock shut, and that changes its state to be occupied. So here's what it looks like. You walk up to the door. Let's say there's nobody there. Let's say the door says vacant or open or available or whatever it says. And the rules are that you can only access the restroom if it's vacant. When you walk in and shut the door, then the sign, the state of the lock, if you will, changes to occupied. So now you're inside the critical section doing your thing. And anybody else who shows up while the restroom is occupied has to wait and kind of queue up. And notice that this is what's called a fully bracketed protocol, meaning that the person or the thread that acquires that resource, acquires the access to this critical section, must be the one to unlock it. So the person on the outside of the door can't get in as long as the door is locked. Once the person in the restroom is done, then they leave and the state goes to vacant again, and then the next person in line can go ahead and enter. So that's just a quick overview of a human known use of a mutex. I'm sure you're familiar with that kind of a protocol. And that's essentially the way that things work for reentrant locks, which we're going to talk about in more detail in the rest of the lessons that are part of this particular section.